See the title slide?
Yes, we can see.
Perfect. So, all right. If anyone still goes to the bank, to take out cash, how many people double check that the machine gave you however much you take out, 10, 20s, or whatever currency you're using, whether euros or dollars or bonds or whatnot, right? Who at the cash register, when we go to the store and there's a total, and you actually still pay the cash, which is not that common anymore, double checks that the computing system on the other side gave you the right change. Who checks things like weights and measurements? We just trust that machines can do a good job of certain things. But are we there when it comes to more sophisticated, what we like to think of as AI, which isn't really a new planet, it's just an extension of things that we've been doing for a long time? And I think the short answer is no. Would you trust your life or a friend's life with a judgment call made by an AI? No. And yet at the same time, we are looking to these systems to do more and more critical tasks with less and less human supervision. So uh, this talk is all about not just trust, but warranted trust, which is to say trust that's been deserved. And I'll explain that term in a little bit in AI-driven systems. So I'm going to spend a few minutes going through some key concepts, by way of introduction, not some generic the importance of AI, but just a few illustrations of the kinds of things we kind of count on or depend on, because that goes part and parcel with the more we depend on stuff, the more we really ought to trust it. And so, what are some examples of where we clearly can't trust? Everyone's heard of hallucinations, but there's all kinds of examples of AI output that leaves you scratching your head, asking, no human would have made that kind of mistake. So what's going on? And then I'm going to introduce something called neurosymbolic computing and a particular variant I call multi-channel neurosymbolic computing as an approach, to resolving what are some of these fundamental issues around trust, and then kind of wrap it up and hopefully have a good little discussion going at the end. So no further ado. All right, some getting some basic concepts down, right? Information, right? We all talk about data, we talk about knowledge, we talk about facts. It doesn't really matter. We've got declarative and or procedural expressions capable of truth testing. Now, declarative ones, it's easy enough to say, right? Can we truth test the temperature? Can we truth test, a long lag coordination? Can we truth test a multiplicative, product? For procedural expression, we're really testing is that the procedure, when properly executed, achieved the claimed result, right? And so if someone tells me to close the door and I leave the door open, I did not truthfully execute that command. Something happened. So we can have that notion of testing applied to either declarative or procedural expression, which is important because a lot of what we're looking at in the AI space are procedures. Did it do the right thing? Computational reasoning, calculating deduced and or inferred quote unquote output information given a collection of quote unquote input information. For example, we may sum a whole bunch of inputs, right? We may take the least squares, of a whole bunch of XY coordinates. We may look for the centroid of a whole bunch of XY coordinates. We may look for the most invariant relation, right? That links a whole bunch of XY pairs together, right? Which is the essence of what we're doing when we're using machine learning to come up with functions, which we then use to do something. So in that sense, machine learning is really a kind of computational reason that computes invariance from information, i.e. from training, that can be used to infer other information, which is what happens in deployment. So we take a bunch of paired images and names, a bunch could be 100, a bunch could be 100 million, right? And now we're going to go off and we're going to give it a new image and we're going to figure out what the name was, right? We have a whole bunch of numeric data. We find a central tendency. We've trained on word sequences and parts of speech. We're now, of course, with with transformers and all their fancy architectures, we can go from word sequences to word sequences. But at the end of the day, you need a trained algorithm. This whole just mind-bogglingly explosive world of Gen AI is still coming out of the same paradigm as the AIML of the last 15 to 20 years. It's way more powerful. It's way more parallelized. It's taking advantage of GPUs in a way that was not possible 20 years ago, but it's the same trained algorithm. We're just kind of doing it in reverse. The IML says, hey, give me a new X. We've calculated the F, and now I'm going to tell you what the Y is, or I'm going to tell you that name. And with a Gen AI, what you're really saying is, spit me out an X, right? A new X that, given my Fs, would have been given this Y. So we're, for all of the impressiveness, we're still in this world of statistical classification. What about AI, right? AI is really capabilities built with ML and information. And information is important because an ML algorithm, right? Take your take your favorite, Mask or CNN or whatever, absent information is pretty inert. Not much going on, right? It's the combination of massive amounts of training data with these algorithms to provide a highly trained algorithms that's actually useful for doing things, whether it's facial recognition, forecasting, intruder detection, or now in this world of the Gen AI, code translation, parsing, program writing, paragraph writing. I've actually been playing around in, you know, some of these new LLMs, they're pretty much like solid college undergrad, which is pretty impressive, if you think about it. So what about trust? Well, trust is really the willingness to act on that output without further verification. If you need to further verify it, you don't trust it. So that all that is going back decades, trust but verify, that doesn't really make sense. That's like saying, go left but go right. No, trust is not verified. Otherwise, and there's all kinds of cases where we need trust, right? You walk into an elevator, you trust that it's going to work. You walk into a skyscraper, you trust it's not going to collapse. You're driving your car, you trust the brakes are going to work. If we were constantly testing all of these bits of machinery, we would never do anything. So, uh, in fact, we think people are mentally unstable if they don't trust everything. So trust is part and parcel with just being human and acting in this fairly complex world. So trust, you can't punt on trust. And what about warranted trust in an AI system? Well, that's trust in the information output based on knowledge of how that output was produced and the attributes of the output itself. That's kind of like statistical process control. So if you go back to the aftermath of World War II and the rise of folks like Deming and Juran, who were looking at manufacturing processes at the industrial scale, they figured out that it's not that efficient to just keep testing the output to kind of do random product sampling, but to actually test the process. And if you have confidence in the process, then that confidence extends to the output. So we basically, to warrant a trust in our system, is we know how it works, right? We know the mechanisms. We trust that that's going to produce an output that warrants our trust. All right. Importance of AI, right? Let's take a look at success in visual recognition, right? We have an image on the left, and we're running mask RCNN, it's been identified to be trained to identify people, running on a security camera, identifying pixels tagged as people, showing true positive. Classic, center of the bullseye, that really seems to work. Right? Go and you say, hey, let me find boys, and amazing job pulling up boys, find toothbrushes. This stuff works. At least it seems to work. Right? So we build all kinds of applications, right? We could build an intruder application. So the little POR is an ontology term, means portion of reality. So a little chunk of reality, there's a person. And our sensors are picking up, certain pixels that are being classified as person. I don't know if you see my cursor. Right. So being classified as person, and in this very simple world, we're in a space where there's not supposed to be any people. It's after hours. There's just no one's supposed to be there. So all people are classified as intruders. So the person is recognized, classified as intruder. That sends a signal to security. Security comes and checks it out. Very simple intruder detection application based on image recognition. All right. What about trust? Well, we got that boy and we got toothbrush. When you query for boy with toothbrush, you can get really different results. Things that no one who understands what boy is or who understands what toothbrush is would ever put these images as boy with toothbrush. So someone could come back and say, well, obviously the algorithm wasn't trained to recognize boy with toothbrush images. But that's the issue. That compositionality that humans automatically have isn't something innate. I'm not saying there aren't algorithms now that haven't been trained that way, but it doesn't come innate. Someone's got to come in ex post facto and say, that's important. Let's not miss that. Let's go add that to the training. Let's make sure that works. But it doesn't natively think that way. It looked at pixels. This is a very real example. I live in Cambridge, Massachusetts, but I go to a little home up in the mountains to get away, and pretty much reliably every weekend. And so I go to the local, gasoline station, buy some gas, head up, and about every 6 months, that gasoline purchase is called a fraud. The credit card is stopped. I'm dealing with the credit card agency. I'm like, guys, is anybody looking at my past history? Is anybody reconciling this one estimate that this could be a fraudulent transaction with 5 years of historical records? No human in their right mind would classify that response as likely fraud. It's at the same gas station for about the same amount on the same frequency. It's crazy, but this happens. This kind of thing happens all the time. You know, buying plane tickets, right? Buy a plane ticket to whatever to let's just say to Athens, and buy a plane ticket from Athens to Hania on Crete, and then a hotel in Crete. That's suddenly now considered to be fraudulent, but it just accepted all the transactions before. It doesn't make any sense. It's statistics. It's not how we think. So, am I going to trust that output blindly? I don't think so. Let's go back to the NASCAR CNN. So now we have a cell phone on a blanket. 94% confidence, NASCAR CNN, trained on a very large volume of data, thought the blanket is a person. That's not a little mistake. No human would ever make that mistake. So how can you trust a machine running at scale when these kinds of mistakes can happen? And I'm sure most of you, have heard, if not seen, there's all kinds of stuff going on. You can take it if someone can reverse engineer the training data that went into a visual classifier, you can sprinkle noise into data such that a human wouldn't notice the difference and a machine is no longer capable of recognizing what's going on. So that's a problem. That's not particularly robust. So where's this coming from? Like, what's the cause? So let's just start off with how does ML look at a person? What's a person to ML? It's a set of pixels similar to training data with the same tag, right? So these are all just images here of, things that have been tagged as people. Okay. Is that how we think? No. For humans, right? Human view of a person is a large two-legged mammal with a rich set of attributes, right? So anything that is true of mammals or living things is going to be true of people. If it's a person, it's got to have a head if it's alive. Certainly, typically has appendages and torsos, and there's some statistical there. Someone could lose a hand or a foot. I mean, yes, there are differences, but on the whole, people have got body parts. People do things, parenting or purchasing or working, breathing, and so forth. And we have relations with other objects. We live or exist inside a building. We wear clothes. We drive cars. We use products. We are bigger than a toaster oven, and so forth. All of that is taken into account somehow by people when we're looking at something and saying, is that a person? So for people, first thing is that data, whether it's visual data or audio data, or olfactory data, or sometimes tactile data, but least of all that, is about the world, right? That image I'm looking at, even with my eyes, forget it on a picture, is about the world. That's what we have. That's what we talk about mirages, right? Or things that fool the eye. In French, c'est trompe l'œil. It's just there's all kinds of expressions for that. And AI data is the world. That chunk of data is what's being analyzed. It is not fundamentally a proxy for the world. It is the world. That is a huge difference. Confidence in the statistical sense is confidence that the pattern currently being classified is similar to a similar pattern seen in training data. And even if visual, man, the world's a lot more complicated than that. So that's a big difference. Second, humans, we extract meaningful features with every sense, right? This world of deep learning it's a mixed bag. For all of the incredibly powerful ability to squeeze associations out of the data, there's also the risk of extracting meaningless features, spurious features that only make sense in that particular data set. Old-fashioned statisticians had a good word for it. It's called overfitting. Now, the response these days is more like, well, as long as we can have every possible observation in the universe, we're never going to get beyond our data. The data will be everything. But that's, of course, never really the case. We're getting closer, but that'll never be the case. So you're always going to have that word, that there were 43 gray pixels in the top left part of the image every time a speeding car was seen in all of my training images. And the machine learned that. It doesn't know what a meaningless feature is. It's just a feature. Third, humans cross-check multiple senses for consistent outputs. We cross-check what our eyes are showing us, with what our ears are hearing, with our nose smells, with what I know from my life's prior experience, from what my buddy told me, from what I read last night in a book. We cross-check multiple senses, what I call channels. There's no real cross-checking. I mean, there can be in an ad hoc way, within the bounds of an algorithm. Of course there is. But there's no principled cross-checking. And there's no principled cross-checking across the features that are within different ML models performed by an external entity. And finally, humans are actually really good at comparing, analyzing, communicating preliminary findings. So you can have people collaborate to solve a problem. That's harder. If you had 4 independently trained ML models, there's no collaboration except in the output. All right. So what about multi-channel neuro-symbolic AI? Where's that taking us? Well, again, humans are multi-channel sense makers. So what does that mean for ML? Well, it might mean that you may have differently trained versions of an algorithm combined with different algorithms. So, let's say 2 differently trained versions of MaskRCNN. You could have now OpenPose, which is another algorithm that looks for joints in the human body. You can compare that with your company's own analytics store. You can compare that with what employees think. There's no limit to that. The question is, you want to reconcile different channels. Any channel that has a kind of an independent view of what could be true should be brought to bear. So channel logic really is the expression that there are many channels that produce representations of this world. There are sensory channels, motor channels, knowledge channels, you give them different names. The ML output from any one channel needs to reconcile with the data or ML output from all relevant channels. So if channel one says that looks like a person, and channel two says that is on top of a toaster oven, there needs to be a conclusion that says that is likely a figurine of a person and not an actual person. So there's, certainly this is not, this is, you can see all kinds of stuff coming out of, DARPA. There's, a lot of places where this kind of thinking is happening. But if we just kind of look at it in the larger framework, from this, from the 1700s through to today, it's statistics. That's really what's going on, right? And for the last 60 years now, it's hard to imagine it's been that long. We have a whole bunch of other stuff, kind of MIS, EIS, management information systems, executive information systems, decision support systems, business intelligence, analytics, all meaning the same thing, right? Just different words for the same thing. Enterprise analytics architectures. We've got rule-based expert systems, which still live, right? And then we had MDDBs and data mining became AIML and Gen AI. And now, of course, we got these LLMs, which are really just an extension of Gen AI, which is still an extension of the ML, which is an extension of statistical classifiers. And in the world of, big waves of AI, this is still Gen 2. It's still statistics. It's still probabilistic. We're moving on to Gen 3. And so there's a lot of work going on in this area. I put in the word adaptive, but neuro-symbolic computing architectures more generally, whether it's just for representation, reasoning, or the whole AGI, whatever you want to. But now you're combining kind of the certainty, the exactitude of symbolic reasoning with the probabilistic aspects of kind of the bottom-up statistical classifier. So you're really going bottom up and top down. And if you think about it, just like an analogy, like when the corporate budgeting is really a reconciliation process where everyone at the bottom says how much they want for next year. And then corporate says how much we got. And they push back and say, you can't have that much. And then say, well, if I can't do that much, then I'm going to only do this. And it's a bottom up, top down, multi-step or multi-cycle reconciliation process. So it feels good. There's a lot of research going on in the space, so there are many, many articles, but we're already now at the survey world. If you take a look at these ones to the right? Neuro-Symbolic AI is taxonomy, a survey towards data knowledge of an AI survey. So there's enough neurosymbolic stuff out there that there's already surveys on. So it's worth being, aware of these various trends. I think that solutions to trust are really coming out of here. And that world, I've done stuff with my little company. We have a new company now called Sensepoint. Blender isn't really operating anymore, but we've been in this space for a while and focusing really on trust. So, for example, if you cross-check mask CNN, which had found a person, and we cross-check that with OpenPose, which is looking for people parts, then we say, we don't think that's a person because we didn't find anything that looks like a person in that. Very basic. Or you can now say the mask CNN plus OpenPose using spatial fusion running on a security camera is fooled into thinking that a TV image is a person. Why? Because it sees the outline of a person. That's the masked part of the mask CNN. All the little dots are OpenPose finding particular joints between the parts of a body, so and features, so eyes and ears and elbows and wrists and so forth. So all of this, we get, wow, I've got the shape of a person. I got all these people parts. Surely I'm dealing with a person. Not quite. Right. So if you are also looking and you see a household appliance like a TV, and you see that this image seems to be inside of the TV, then you can make perhaps the more educated conclusion that that's probably a TV image of a person. I think if you were to, you can see a core score, person not real. So core score was something we gave to our cross-checked output. So we can now take these days. My group, we're doing a lot of stuff with autonomous systems. You can do that for, just all kinds of industrial purposes and other purposes for doing it. So autonomous systems to date, seems very super advanced, but it's not quite as advanced as you might think. So motion control, we've got a great job of, right? So self-driving cars, right, or self-driving boats or self-driving planes, we're much, much closer to autonomous device control, obstacle avoidance. So give me an address, give me a viable roadmap, give me the rules of the road, and now we have a car that can, on average, get us from point A to point B. That's great. So now that you can move, you can also ask the question, what about if I want to learn something? So the question isn't, can you get me to address X? It's where should I go and why? And so we're in the world of embodied knowledge acquisition, where you're tasking an autonomous device to go off and learn something. Survey the coast, compare it with prior maps, see if there's any damage to the bridges. Are there any damages to underwater pipes? What's a typical pattern of traffic in this harbor? Anything that involves what I call embodied, because it's a real device, right? Out in the world, acquiring knowledge. And so that basically now is a third layer that interacts with the device control layer. So it sucks in communications, it sucks in telemetry, it sucks in sense data. And if we're dealing with boats, it spits out waypoints. Waypoint is a spot that you're telling the boat to go to. And sensor commands, which may mean, hey, rotate that camera, or send out a request, So the kind of things that you've got to do, right? You got to unify sense data, and you have to locate detected objects in the world. Not on my, so that's a big thing, right? A classifier detected a pattern as being, a sailboat, but what you first get back is a bounding box telling you where that sailboat image is in your larger image frame. I don't care about that. I want to know where's the boat in the world. Is that 5 feet in front of me? Is that 5 miles in front of me? Where's the boat? Is that even possible, right? So we have to go from that concept of training data more to reconciling things with the world. And then you have to reconcile what the sensors are telling you with what you think is true. That's that pending observations with prior knowledge to kind of come up with some sense of warranted trust. And you got to be able to take a look at that and analyze that and realize maybe what we thought we knew about boats was wrong, and so forth. So it's not a deterministic system, but it's based on really trying to figure out how many channels can you reconcile to improve this warranted trust. So goals of these can be, improve the warranted trust, right, in our classifications by reconciling with prior knowledge, by moving oneself, get a go better look on it, right? By changing your sensors or by getting others to modify where they are. All right, in conclusion, AI is increasingly relied upon for providing information, performing tasks whose correctness we need to trust. Warranted trust comes from having transparently reconciled across multiple independent channels of information. Current generation AI architectures lacks a principled notion of information channel and therefore lacks warranted trust. To solve this problem, new AI architectures based on third generation Neuro-Symbolic computing paradigms will need to be deployed. Thank you.
Are there any questions? Thank you very much for your great presentation, Mr. Erik.
You're welcome. Thank you.
Our next speaker is Professor